Good day everyone. In today's video, we are going to talk about hypothesis testing. So first, we are going to define what is hypothesis and hypothesis testing. So hypothesis is simply a statement that something is true. It is also a tentative explanation, a claim, or assertion about people, objects, or events. Hypothesis testing is a procedure in making decisions based on a sample evidence or probability theory used to determine whether the hypothesis is accepted or rejected. So there are two types of hypothesis. First is the null hypothesis. It is denoted by H sub O. The capital letter H stands for hypothesis and the subscript 0 implies no difference. This is usually designated by a not or no term in the null hypothesis, which means there is no change. The next one is the alternative hypothesis. It is a hypothesis to be considered as an alternate to the null hypothesis. The symbol H sub A read as H sub A is used to stand for the alternative hypothesis. So there are two types of errors, the type 1 and the type 2 error. So in type 1 error, rejecting the null hypothesis when in fact the null hypothesis is true. It is also known as the alpha error. The type 2 error is not rejecting the null hypothesis when in fact the null hypothesis is false. It is also known as the beta error. So here you can see in this table the four possible outcomes for a hypothesis test. In hypothesis testing, four outcomes are possible, two of which lead to incorrect decisions. Based on the table, incorrect decisions occur if either a true null hypothesis is rejected or false null hypothesis is accepted. The false incorrect decision is called type 1 error and the second is a type 2 error. The next one is the level of significance. It is defined to be the probability of committing a type 1 error. This is the probability of rejecting the null hypothesis. The choice of level of significance depends on the statistician or researcher who is willing to commit a type 1 error. Statisticians commonly use 1%, 5%, or 10%. Using 0.05 level of significance in testing hypothesis implies that the probability of accepting to commit an error in rejecting the null hypothesis is 5%, but 95% sure that the decision made is correct. So this drawing here represents the rejection region and the non-rejection region. So one-tailed and two-tailed test. One-tailed test is used when the alternative hypothesis is directional, which means that the value of the measures is either greater than or less than the other measure. Two-tailed test is used when the alternative hypothesis is non-directional, which means that the values of two measures of the same kinds are not equal. So here, signs in alternative hypothesis and the rejection region. So in two-tailed test, it is not equal, so both sides. In right-tailed test, it is greater than, so it is right side, and left-tailed test, it is lesser than, so it is in the left side. For example A, this shows the left-tailed test, and the example B shows the right-tailed test, and the example C shows the two-tailed test. So critical region in testing hypothesis. So level of significance and type of test. So at 0.05 left-tailed test, Z is lesser than negative 1.645 and right-tailed test is Z is greater than 1.645 and so on. So some terminologies to remember. First, here is test statistic. The statistic used as a basis for deciding whether the null hypothesis should be rejected. The next one is the rejection region, the set of values of the test statistic that leads to rejection of the null hypothesis. And the non-rejection region, the set of values of the test statistic that leads to non-rejection of the null hypothesis. The last one is the critical value or the values of the test statistic that separates the rejection and non-rejection regions. So this is the procedure in hypothesis testing. First is you need to formulate the null and alternative hypothesis. Next, you need to decide the level of significance. Next is choose the appropriate test statistic. Next is establish the critical region, compute the value of the statistical test, decide whether to accept or reject the null hypothesis, and the last one is draw a conclusion. So now we go here to the hypothesis about means, comparing sample mean and population mean. So here the first equation shows the sample mean, and the next equation shows the population mean. So the z here, the equation is the z test value, the x is the sample mean, the it seems like a letter U. It is the population mean or claimed mean in null hypothesis in the standard deviation or population standard deviation. S stands for sample standard deviation. N stands for number of cases greater than or equal to 30. So example, problem 1. The treasurer of a certain university claims that the mean monthly salary of the college professor is 21,750 with a standard deviation of 6,000 pesos. A researcher takes a random sample of 75 college professors who were found to have a mean monthly salary of 19,375 pesos. Do the 75 college professors have lower salaries than the rest? Test the claim at standard deviation of 0.05 level of significance. Apply the different steps in testing hypothesis to solve the given problem. Solution. First, we need to determine the null and the alternative hypothesis. So our null hypothesis is the mean monthly salary of the college professors is 21,750. And our alternative hypothesis is the mean monthly salary of the college professors is lower or less than 21,750 pesos. So here's the solution. Step 2. Our level of significance is 0.05. Step 3. We need to use one-tailed tests because our alternative hypothesis is directional. The first step is the tabular value or critical value of z at 0.05 level of significance is 1.645. Then compute the z value. So in computing the z value, we need first we need to determine the given. So x is equals to 19,375, and then our next is 21,750. Our standard deviation is 6,000. Our n is 75. So we need to follow this equation. X minus the mean over standard deviation over square root of n. So then we need to fill in the given. So 19,275 minus 21,750 over 6,000 over square root of 75 is equals to negative 2,375 over 6,000 over 8.66. Then we need to simplify. It will now become negative 2,375 over 692.84. Then we need to just simply divide it. The answer is negative 3.43. So step 6, the computed value of z is negative 3.43, lies under the rejection region. Therefore, reject your null hypothesis and accept your alternative hypothesis. So our conclusion is the mean monthly salary of the college professors are in lower than 21,750. The next one is the difference between means or the sample means. So by following this equation, we can solve this problem. So z is equals to x sub 1 minus x sub 2 over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. So our x sub 1 here is the mean of the first sample. The x sub 2 is the mean of the second sample. Our s sub 1 squared is the variance of the first sample. As our S sub 2 squared is the variance of the second sample. N sub 1 is the number of cases in the first sample, and N sub 2 is the number of cases in the second sample. So, for example, a sample of 70 observations is selected from a normal population. The sample mean is 2.78 and the sample standard deviation is 0.83. Another sample of 58 observations is selected from normal population. The mean sample is 2.63 and the sample standard deviation is 0.75. Test the hypothesis using the level of significance 0.05. So, solution. Step 1. We need to determine our null and alternative hypothesis. So, our null hypothesis is our x sub 1 is equal to our x sub 2. Our alternative hypothesis is our x sub 1 is not equal to our x sub 2. So, step 2, our level of significance is 0.05. And in step 3, the alternative is expressed in a non-directional statement. Therefore, we will use the two-tailed test. And then the fourth step is the tabular value of z at 0.05 is equal to positive or negative 1.96. Step 5, we need to compute for the z value. So, our given, our x sub 1 is 2.78, our S sub 1 is 0.83, our x sub 2 is 2.63, our S sub 2 is 0.75, our N sub 1 is equals to 70, our N sub 2 is equals to 58. So, we just simply need to follow this equation and fill in the given to this equation. So, 2.79 or 78 minus 2.63 over the square root of 0.83 squared over 70 plus 0.75 squared over 58. So, it is equals to 0.15 over square root of 0.01954. So, it is equals to 0.15 over 0.1298. Our z value is equals to 1.07. So, the computed value of z is equals to 1.07 lies under the non-rejection region. Therefore, accept the null hypothesis. Our conclusion is there is no significant difference between the two samples. The next is hypothesis testing about a single proportion. So we need to follow this equation. P sub 1 minus P sub 2 over the square root of P sub 1 times 1 minus P sub 2 over N. So our P sub 1 is a population proportion and our P sub 2 is sample proportion, and then N is number of cases. So problem number 3. A barangay captain claims that at least 85% of the residents in his barangay have household pets. To test this claim, a researcher randomly selected a sample of 550 residents and find that 495 of them do have household pets. At 0.05 level of significance, what can you conclude? So first, our null hypothesis is P is greater than or equal to 85%, and our alternative hypothesis is P is greater than 85%. Step 2, our level of significance is 0.05. Step 3, alternative hypothesis is expressed in directional statement, therefore use one-tailed test in this problem. The tabular value of Z 0.05 is positive 1.96. So compute the Z value. So P, what is our P here? So P is 495 or 550 minus 0.85 over the square root of 0.85 times 1 minus 0.85 over 550. It is equal to 0.05 over the square root of 0.00023181818. It is equal to 0.05 over 0.015225576. Our Z value is 3.2. 3.28. So the computed value of z is 3.28 lies at the rejection region. Therefore, reject the null hypothesis and accept the alternative hypothesis. So our conclusion is there is a difference between the two proportions. The next one is hypothesis testing about two proportions. So z is equals to p sub 1 minus p sub 2 over the square root of p sub 1 times 1 minus p sub 1 over n sub 1 plus p sub 2 times 1 minus p sub 2 over n sub 2. Our p sub 1 is the proportion of the first sample. Our p sub 2 is the proportion of the second sample. Our n sub 1 is the number of cases in the first sample. And n sub 2 is the number of cases in the second sample. For problem number 4. A researcher made a survey regarding the population of male and female college students who dropped their business mathematics subjects before midterm examination. In a sample of 600 female students, 49 dropped their business mathematics subject before midterm examination. In a sample of 450 male students, 36 dropped their business mathematics subject before the midterm examination. Is there a difference in the proportion of male and female students who dropped their business mathematics subjects? Use a level significance of 0.05. So our solution is, first, our null hypothesis is p sub 1 is equal to our p sub 2. And our alternative hypothesis is p sub 1 is not equal to p sub 2. Our level of significance is 0.05. And then step 3, we will use two-tailed test because each A is non-directional. Step 4, the critical or tabular value of z at 0.05 is equals to 1.96. Then compute the z value using the equation. So first, our p sub 1 here is 49 over 60, and our p sub 2 is 36 over 450, n sub 1 is equals to 600, n sub 2 is equals to 450. Solution. Follow this equation and substitute the given. So 0.0817 minus 0.08 over the square root of 0.0817 times 1 minus 0.0817 over 600 plus 0.08 times 1 minus 0.08 over 450. It will now become 0.0017 over the square root of 0.0028599745. Our z value now is 0.10. Step 6a is the computed value of z is 0.10 lies at the area of non-rejection. Therefore, accept the null hypothesis. Conclusion is there is no significant difference between the two sample proportions. Note, when the sample size involves small cases or n is less than 30 and the population standard deviation is unknown, use the sample standard deviation as an estimator of population standard deviation. In case like this t distribution as test statistic, it is always an assumption that the sample population is normal or approximately normal. The t distribution was developed by an employee of Irish Brewery in the person of William S. Gossett. He chose to publish his findings using the pen name student. To honor his work, the distribution is known today as student t distribution. Next, we will proceed to the test concerning means. Compare sample mean and population mean. So our t is equals to x minus our mean over s over the square root of n. Our t is our t value, x is sample mean, the next is the population mean, s is our sample standard deviation, and number of cases less than 30, and our df is equals to n minus 1. So example, problem 5. According to the Department of Education, high school teachers work an average of 40 hours per week during the school year. A district supervisor of a certain school surveyed 28 randomly selected teachers and found that they work an average of 42.6 hours a week. The standard deviation was 3.75 hours. Test if the mean number of hours worked by teachers in the supervised school district differs from the national average. Use level significance of 0.01. So first, our null hypothesis is Our population mean is 40 hours. Then our alternative is population mean is not 40 hours. Step 2, our level of significance is 0.01. Alternative hypothesis expresses a non-directional statement, therefore we will use the two-tailed test. Step 4, if one sample is given, use dfn is equals to n minus 1. So df is equals to n minus 1, or n is 28 minus 1, or df is now 27. The tabular value of t is 2.771. Step 5, compute the t value. Given our x is equals to 42.6 hours. Our population mean is 40 hours. Our a is 3.75 hours. Our n is 28. Solution, we need to substitute the given to this problem. So 42.6 minus 40 over 3.75 over the square root of 28. So it will become 2.6 over 3.78 over 5.2915. It will now become 22.6 over 0.7027. Our t value now is 3.67. So the computed value of t is equals to 3.67 is greater than the tabular value of t is equal to 2.771. Thus, reject the null hypothesis and accept the alternative hypothesis. The conclusion is there is a significant difference of the working hours of 28 teachers per week compared to the national average. So now we proceed to the difference between means. T-test for dependent samples. T is equals to x sub 1 minus x sub 2 over s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2, where x sub 1 is our mean of the first sample, x sub 2 is the mean of the second sample, s sub 1 squared is the variance of the first sample, s sub 2 squared is the variance of the second sample, n sub 1 is the number of cases in the first sample, n sub 2 is the number of cases in the second sample. Our df is n sub 1 plus n sub 2 minus 1. Next is a t-test for dependent samples. So t is equals to d over s over square root of n. S is equals to square root of the sum of d squared minus the square of the sum of d over n minus 1. So d is the difference between means. Next is the sum of the square difference. Next is the sum of the mean difference. N is the number of cases. S is standard deviation. df is equals to n minus 1. So for example, an agronomist randomly selected 20 mature calamansi trees of one variety and have a mean height of 10.8 feet with standard deviation of 1.25 feet, while 12 randomly selected calamansi trees of another variety have a mean height of 9.6 feet with a standard deviation of 1.45 feet. Use a level significance of 0.05. So step 1, our null hypothesis is x sub 1 is equals to x sub 2. Our alternative hypothesis is x sub 1 is not equal to x sub 2. Our level of significance is 0.05. The alternative hypothesis is non-directional, thus we'll use two-tailed test. Since there are two samples used, df is equal to n sub 1 plus n sub 2 minus 2. So 20 plus 12 minus 2 is equal to 32 minus 2, or df is 30. The tabular value of t is 2.0.42. So step 5, compute the t value given x sub 1 is equals to 10.8 feet, x sub 2 is equals to 9.6 feet, s sub 1 is equals to 1.25 feet, s sub 2 is equals to 1.45 feet, n sub 1 is equal to 20, and sub 2 is equal to 12. Then we will going to substitute the given to the formula. So 10.8 minus 9.6 over the square root of 1.25 squared over 20 plus 1.45 squared over 12. It is equals to 1.20 over the square root of 0.252222. It is equals to 1.20 over 0.502222. Our t value is 2.38. So the computed value of t is 2.38 is greater than the tabular value of t, 2.042. Thus, reject the null hypothesis and accept the alternative hypothesis. Our conclusion is there is a significant difference between the two samples. So problem 7. Professor Leonardo A. Gabuyo conducted a review in his BM 102 class. He gave an examination before and after the review and gathered the following data. So student 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 score before review, then score after review at a level significance of 0.05. So is the review class effective? So here, solution. Our null hypothesis is there is no significant difference between the mean score of the students before and after the review class. So HA is there is a significant difference between mean scores of the students before and after the review class. Our alternative hypothesis is 0.05. So we will use two-tailed test because our alternative hypothesis is non-directional. The tabular value or critical value of T is equal to 2.262 where DF is equal to 9. So compute the T value of dependent sample. So here, in computing this, we will just simply minus our score before review to the score after review. For example, 16 minus 18 is equal to negative 2. 8 minus 12 is negative 4. Then that is our D. Then our D squared is the square of our D. So 2 to the power of 2 is equal to 4, and 4 to the power of 4 is equal to 16. So we just simply need to add our D, and we simply need to add our D squared. So our D is equals to 13, and our D squared is equals to 93. So then follow this equation. Our S is equals to the sum of D squared minus the sum of D squared over n minus 1. So it will now become the square root of 93 minus negative 13 squared over 10 over 9. So 93 minus 16.9 over 9. So the square root of 8.4555556 is equals to 2.91. The next step is follow this equation. D over S over square root of n. So our D is equals to 1.3 over 2.91 over the square root of 10. So 1.3 over 0.920222799. Our T is equals to 1.41. So the computed value of T is 1.41, which is less than the tabular value of T 2.262. Therefore, accept the null hypothesis. Conclusion: there is no significant difference between the mean scores of the student before and after a review class. It implies that the review was not effective. Now we will go to the chi-square goodness of a test equal expected frequency. So the chi-square goodness of a test equal expected frequency. When the data are nominal or ordinal, the hypothesis test used in this type of data is called non-parametric or distribution-free test. This implies that these tests are free of assumption regarding the distribution about a population. The chi-square goodness of fit is one of the most commonly used non-parametric tests, which was developed by Carl Pearson. The purpose of the goodness of fit test is to determine how well an observed data fits unexpected data. So we will follow this equation. X squared is equal to the sum of O minus E squared over E, where X squared is equal to our chi-square value, or O is the observed frequency and E is expected frequency. For example, there are 3 gates at the University of the East. The building maintenance supervisor would like to know if the gates are equally utilized. As an experiment, 600 students are observed as they enter the school. The number of students using each gate is reported below. At 0.01 significance level, can we conclude that there is a difference in the use of the 3 gates? So the name of the gates is the Recto, Lepanto, and the Gastambili. Number of students And the first gate is 245, the second gate is 205, and the third gate is 150, the total of 600 students. So because there are 600 students in the sample, we expect that 200 students fall in each of the three categories. These categories are called cells. So our E is 200, 200, 200. It is also equal to 600. So solution, step 1, we need to formulate our HA and HO. Our HO is there is no difference between the set of observed frequencies and the set of expected frequencies. Our alternative hypothesis is there is a difference between the set of observed frequencies and the set of expected frequencies. Our level of significance is 0.01. The test statistic is the chi-square distribution. Is designated as x squared and is computed by x squared is equals to the sum of O minus E squared over E, with k minus 1 degrees of freedom, where k is the number of categories and O is an observed frequency in a particular category. E is an expected frequency in a particular category. So we need to substitute our given to this formula. So sum 245 minus 200 squared over 200 plus 205 minus 200 squared over 200 plus 150 minus 200 squared over 200. So it will now become 2025 over 200 plus 25 over 200 plus 2500 over 200. Then it is equals to 10.125 plus 0.125 plus 12.5. Our x squared is now 22.75. In step 4, formulate the decision rule. Computed value of x squared is equals to 22.75. Our critical value of x squared is 9.210. Our DF is 2. Our level of significance is 0.01. Since the computed value of x squared is 22.75 is greater than the critical value of x squared is equals to 9.210, you need to reject the HO and accept HA. So our conclusion is there is a large difference between the set of observed frequencies and set of expected frequencies. Three gates are not equally utilized. So, contingency table analysis. When we applied the goodness of fit test previously in this chapter, we were concerned with only a single variable and a single trait. The chi-square distribution can also be used when we are considering two traits. For example, a number of employees at a large chemical plant were asked to indicate a preference from one of the three pension plans. The results are given in the following table. Is there a relationship between the pension plan selected and job classification of the employees? Use 0.05 significance level. So here are the datas. And plan A, 20, our ESG 34.67. Then next, our DF is a number of rows minus 1 times number of columns minus 1. So DF is equal to R minus 1 minus C minus 1. Expected frequency for a cell is equal to row total times column total over grand total. Expected frequency for a cell is equal to 210 times 104 over 660 is equal to 34.67. 210 times 236 over 660 is equal to 78.67. 220 times 120 over 660 is equal to 106.67. Solution. Step 1, our HO is there is no association between the job classification of employees and their selected pension plan preference. Our HA is there is an association between the job classification of employees. Our standard deviation or level of significance is 0.05. Then compute the x squared. So our x squared is, as what you can see, the solving here. Just watch this. X squared will now become 6.21 plus 21.03 plus 28.70 plus 9.57 plus 25.92 plus 6.80 plus 58.55 plus 2.91 plus 8.40. Our x squared is equals to 168.09. Our computed value of x squared is equals to 168.09. Our critical value of x squared is equals to 9.488. Our DF is equals to 4, and our levels of significance is 0.05. Since the computed value of x squared is equals to 168.09 is greater than the critical value of x squared is equals to 9.488, you need to reject the null hypothesis and accept the alternative hypothesis. Our conclusion would be job classification is associated to the pension plan preference of employees. That would be all for this afternoon, and thank you for watching and listening, and I hope you have learned something from this video. I am Adonis G. Cabo Jr., your reporter for this day. Thank you and God bless.